Okay, this is the pre-lab or pre-lecture, pre-class lecture for Friday, the September 14th. The material here is not going to be as extensive as it was for Wednesday, and so part of the period we can use on Friday for going over continuing lingering issues on naming. So come on Friday, if you have any questions about the naming, or we may do a few more naming problems. But what was on the schedule for today is to talk about the idea of the physical properties and the beginning chemical properties of alkanes. So let's start with the idea of polarity. Alkanes we consider to be nonpolar molecules because they contain only carbon and hydrogen. And so basically our hydrocarbons we consider to be nonpolar because there's very little very little electronegativity difference between carbon and hydrogen bonds. So if you look at ethane, for instance, the electronegativity of carbon is 2.5 versus the hydrogen at 2.1. And so these are very weak, very weakly polar bonds to the point where we consider them to be what we would call relatively nonpolar covalent bonds. Now, if we were to assign the bond dipoles, the hydrogens would be slightly positive, the carbons would be slightly negative, and we will use this small polarity difference a couple of times during the course of the year. But if we're looking at the polarity of a hydrocarbon, we consider it to be nonpolar because this difference just isn't that much. And of course, if you have a carbon-carbon bond, then you have a purely covalent bond, so there's no unequal sharing at all. So alkanes are considered to be nonpolar molecules. And there's lots of examples of alkanes. Um, the really long-chained alkanes make up things like waxes and oils, and we know that they don't dissolve in water because of the fact that they are nonpolar. Okay, and so we have the relatively nonpolar carbon-hydrogen bonds and the purely nonpolar, purely covalent carbon-carbon bonds. And so we saw this slide on Monday, the idea of the homologous series where you build up your straight-chained alkanes one at a time by adding a carbon. And so these are the straight chained. We learned about branch chained on Wednesday because those are the chains with substituents, with substituent groups off of them. But now let's talk a little bit about the idea of the physical properties of straight chained versus branch chained alkanes. And so here are examples of some branch chained butanes and pentanes. Now, I didn't talk on Wednesday for the pre-lab lecture about the common naming of alkanes. We did talk a lot about common naming of alkyl groups, but there are some alkanes that do have common names, and particularly the branched ones. So for instance, this is called isobutane. Again, in the common name system, the total number of carbons is what gives you that quote-unquote parent name. And so here we've got isobutane because I've got 4 carbons and I have my CH3CH group, which we call on Wednesday the iso group. Here's isopentane where I've got CH3CH and I've got 5 total carbons, again another branched. And here's neopentane, which was the new pententane when it was discovered, and we've got 4 CH3 groups attached to this carbon. And so these 3 molecules, these 3 alkanes, have slightly different shapes, and they're certainly different than their straight-chained counterparts. Now, when we talk about the idea of alkane physical properties, we already know that they're nonpolar, they don't dissolve in water, but let's talk a little bit about their intermolecular forces that they can undergo with themselves. And so in the homologous series you see for methane, ethane, propane up to decane, the first thing that you see is that the boiling points increase as you add another carbon to the straight chained. So methane boils at minus 162 degrees. Well, methane is a gas. unless you get down to that low temperature. And so methane and ethane and propane and butane are all gases at room temperature. The boiling point increases as you add a carbon to the chain. That continues on with pentane, which is the first liquid alkane, and then hexane's boiling point increases more, then heptane's around 98, and then you continue on down the line. So the heavier the molecule, the higher its boiling point. And that kind of makes sense, because if we go back to general chemistry and we view the whole idea of boiling point, we'd have to go back and remember the Chang definition of boiling point, which is that that's the vapor pressure at 1 atmosphere of pressure, the temperature is required of the liquid to generate 1 atmosphere of vapor pressure in a closed system. But on the sort of kinetic molecular theory, what's happening is that your liquid molecules have enough kinetic energy to escape into the gas. And of course, this is in a closed system, a dynamic equilibrium where the gas molecules then go back into the liquid. So kinetic energy, of course, plays a role in the boiling point. And so when we talk about kinetic energy, we're talking about 1/2 the mass times the velocity of the molecule squared. So the idea here is that as the mass of the molecule increases, it's going to take more kinetic energy. It's going to take a higher temperature to give those molecules enough kinetic energy to go into the gas phase. And so when we're looking at intermolecular forces, we have to realize that as the molecular weight increases, in general, you're going to have an increase in boiling point. Now, the in general part is that those molecules still have to undergo the same intermolecular forces. We can't compare two molecules where one is hydrogen bonding versus one that has just dispersion intermolecular forces. So in this case, the boiling points are increasing because of the molecular weight. All of these have dispersion forces with themselves. And so that's one thing that goes into the boiling point of the alkanes. And eventually you would get to a mass where that alkane would eventually become a solid at room temperature. So if we're going to compare straight-chained and branch-chained alkanes, we need to make sure that we compare alkanes of the same molecular weight. So here are 3 isomers of pentane. We've got pentane, the straight-chained hydrocarbon, we've got isopentane, and we've got neopentane. So all 3 of these have the same molecular weight, and so therefore any difference in boiling point we can say is due to the intermolecular forces that these molecules undergo with each other. And you'll notice that the boiling point of N-pentane is 36 degrees Celsius, it's 30 of isopentane, and it's 9.5 at neopentane. And so if you look, what's happening? We're going from a straight chained to a branch to an even more branched. So we draw the conclusion that increased branching decreases the boiling point of the alkane. And why is that? What is it about the branching that causes what we could conclude to be a decrease in intermolecular force between 2 branched molecules versus a straight chained alkane? And so in order to look at this, we have to look at the molecular shapes of these alkanes. So let's do that with pentane, the straight-chained hydrocarbon, and isopentane. Now, this slide I'm using is about 20 years old, and so I call van der Waals forces. That term has fallen out of vogue. These are what we call the dispersion forces nowadays, or induced dipole. But if you look at the forces that occur between molecules, it turns out that the induced dipole forces are actually they're proportional to the amount of surface area that the molecules can come in contact with. And so if you have 3 pentane molecules sort of in contact with each other, you can see that there's a large surface area here. And so there's a lot of places for the induced dipole attractions to occur. The more spherical or the less straight or less straight chain the molecule, the more spherical it becomes and the less surface area that you have coming in contact. So the addition of a methyl group here on a 4-carbon chain causes this molecule to become a little bit more spherical and not a straight chain pentane. We have less surface area for interaction, and so we see a boiling point decrease of 6 degrees. Okay, and so if I went to now the neopentane, which almost looks like a sphere, it's so spherical in its shape, those two spheres have very little surface area to come in contact with, and so there you see the boiling point take a huge drop from 30 to 9.5 degrees, and so here we can see there are weaker dispersion forces because there's less contact area. So straight chained alkanes are, if we're comparing same molecular weight, the straight chained alkanes have a higher boiling point than the branch chained, and the more branching you have, the lower the boiling point, because in the straight chained alkanes you've got a lot of surface area for the induced dipole interactions, and as the molecule gets more and more spherical, you have less surface area and less and weaker induced dipole forces. Now, the next section they talk about are sort of the uses and sources of alkanes. And most functional groups, we talk about how you can convert another functional group into and make that particular functional group that we're talking about. Alkanes are a little different because alkanes are found primarily in nature from natural sources. The primary source of alkanes is either natural gas or crude oil. When we talk later on next semester about aromatic compounds, which were the 6-membered rings with alternating single and double bonds, the original sources for the aromatic compounds were coal. Coal contains a high percentage of aromatic compounds, or of the arene functional group. But alkanes can be found mostly in the crude oil. And so crude oil has things like alkanes, a little bit of alkenes, and then alkynes. And so if we look at the first 4 alkanes in the homologous series, methane, ethane, propane, and butane, those can be found in nature in natural gas deposits. Now, 10 years ago, I would have said that most of your natural gas deposits are associated with a petroleum reserve, but nowadays, if you live in Pennsylvania, Ohio, or West Virginia, and in some places out west, the idea of the shale gas, where you can get the natural gas from the shale deposits, is becoming a larger and larger source of natural gas, and potentially a huge source of natural gas. So natural gas contains mostly methane, and that does have a little bit of ethane, propane, and butane with it, as well as some other molecules. And actually, one of the differences in the shale gas that you find in Pennsylvania or West Virginia and that's the Marcellus versus like the Utica shale in Ohio, is that they have hopes that the natural gas deposits in the Utica shale, which is in Ohio, actually has a lot more of these higher order hydrocarbons, which these things can be turned into chemicals and starting materials for all sorts of things like plastics, and so it may be a slightly different source of natural gas. But that's the primary components of natural gas, and we use methane in all sorts of things. We use methane as the natural gas source. We use it to heat our houses. There are some vehicles that run on natural gas, and in places like California, they generate most of their electricity not through coal, but through natural gas-fired power plants. And actually in Ohio and Pennsylvania, the utility companies are looking seriously into changing over some of their coal-fired power plants into natural gas ones, anticipating potentially the natural gas being available from the shale. we also have then, usually associated with that is petroleum. And so we go into the ground and we drill out the petroleum, and we either do that on land or we do it in the ocean. Um, and then we get basically crude oil that we can send to a refinery to be refined. And so there's lots of products that come from a 55-gallon drum of petroleum. It turns out that the major portion, at least it was a few years ago, of the oil that comes in a 55-gallon drum, um, is used for transportation. So cars, jet fuel, diesel fuel. Most of the crude oil is used for transportation, and then there's a certain portion that goes to use for things like fuel oil that some people use to heat their homes and other chemicals. Some of the petroleum is used for specialty chemicals, and the dregs of it, the stuff that's at the bottom that's really heavy molecular weight, can be used as asphalt that we use for paving roads. But you can't do anything with crude oil unless you send it to the refinery. Here's my favorite refinery. It's the one that I grew up living a couple of blocks from. My mother's house would be about here in this picture. And so the front porch overlooks this beautiful refinery that's sitting on the upper part of the Allegheny River. And in the refinery, then we have all of the processes that are used to convert all of that crude oil into the different products, whether it be diesel fuel or gasoline or fuel oil, depending upon what specific processes are going on in that particular refinery and in that particular part of the refinery. And so to sort of simplify this, what you can imagine is, this is my crude picture of one of those towers, is you take the crude oil and you can kind of refine it, at least in a crude sense, by simple distilling. And so you can distill the material sort of like what you did in lab. And the first compounds, the lowest molecular weight compounds from about C5 to C11, are what we use for our gasoline. When you go to the gas station, you fuel up and you see that it has a certain octane rating. Well, that would be based on the amount of energy that's produced for a particular molecule, which happens to be an isomer of octane. It's actually not N-octane. But the first set of compounds after, of course, the natural gas, the gaseous products, we have things, the low molecular weight stuff, low boiling stuff, are the gasolines. And then next, the heavier stuff are what makes up the kerosenes. So if you had a kerosene stove, then you would have a little bit higher molecular weight stuff. And then the third are what corresponds to the heating oils. And so the heating oils, there are some places, particularly in the Northeast, in the New England area, they use heating oil to heat their houses. And so there's always an issue every year that refineries have to turn over their gas production. They have to concentrate more on heating oil production for the Northeast. And so there's usually a little spike in gasoline prices because the gasoline is not produced in the quantity when those refineries change over. But your heating oils are C14 to the C25 fragments, and so they have fairly high boiling points. And then once you distill off those, then you're into compounds that have very high molecular weights and very high boiling points. The things that would be used for lubricating oils and waxes, very long-chained hydrocarbons. And what happens there is that you can only distill those if you reduce the pressure on the system. And so when you reduce the pressure, you reduce the vapor pressure that's needed to become a gas, and therefore you reduce the temperature. And so you can distill those off. And then anything that's kind of not left over or left over that doesn't distill can be used in paving roads as sort of asphalt type material. It's not as simple as just taking the stuff that's left over and putting it onto roads. There's a lot of chemistry that goes into that as well. So really, our transportation, the transportation that we use, at least in this country, is heavily dependent. The gasolines and the kerosenes, those are definitely fueled by crude oil. and then some of these other products are also energy related. And then there is a certain fraction of these chemicals that go off that are used to make plastics and used to make precursors for drugs and for other organic molecules. Okay. So that's kind of what the sources of the alkanes are. They're pretty much natural sources. Now, one of the things that the refineries do is they will take very long chained hydrocarbons, and depending upon the particular catalyst that's used, and catalysts have been developed for a number of these processes, they'll take a particular catalyst and do what's called cracking. And so depending upon the particular catalyst, they might have a catalyst that will break a long chain molecule up into maybe 10 carbon pieces. And so when they crack the hydrocarbons, they basically take a long chain and convert it into smaller chains or for whatever product is needed at the time. And so that's why you'll see, for instance, in the fall when they start cracking into heating oils, that requires a different process than cracking into the shorter chain gasolines. And so that's why they'll always say, well, the gas prices are going up because the refineries are changing over to heating oil for the winter. So that's sort of what happens in the refining process. That's a really oversimplification of that. Now, the last thing are reactions of alkanes. And we'll talk in gory detail about one of the reactions of alkanes in the next chapter, or in the next couple chapters. But there's really only two reactions of alkanes that are important. The first is to take our CnH2n plus 2 molecule, react it with oxygen gas in the presence of a flame or a spark, and do combustion. Remember from general chemistry, combustion is the reaction of something with oxygen. It's a redox reaction. And so in the case of combusting an alkane, we make carbon dioxide and water. And so the process of combustion leads to CO2 formation. If you've taken a biology class, either here or high school, you know about the quote-unquote evils of CO2 and the effects of CO2 in terms of absorbing heat and leading to the greenhouse effect, which is good because otherwise we'd be Venus and have a minus 150 some degree temperature, or have it be too hot. But in too much excess, then we can have extreme temperatures, and I'm not going to get into that controversial topic. But that's the combustion, and that process is used for alkanes, and we use it if we drove our car here. We use it to heat our homes, all sorts of things. The butane that you use to light a lighter is combustion. But for the most part in organic chemistry, while this combustion reaction is important, it's not necessarily useful, because in organic chemistry what we'd like to do is to build up molecules. We'd like to take and build a carbon-hydrogen skeleton and hang functional groups off of it. Those functional groups then allowing us to make drugs, or allowing us to make plastics, or allowing us to make new materials. And so what we're going to spend most of our time this year talking about is how you convert one functional group into another. And the alkanes are just kind of the skeleton by which we hang these functional groups off of. So combusting the alkane is useful, but it's not that useful in an organic sense. We will talk about in the next couple of chapters taking the hydrogen of an alkane and reacting it with a halogen like chlorine or bromine, and then doing a substitution reaction where we substitute the hydrogen for either a bromine or a chlorine, and then making an HCl or an HBr molecule. and doing a substitution reaction where we replace the hydrogen on the alkane with a chlorine. And that turns out to be important because I can turn this chlorine into things like OH groups, or I can bond another carbon to it. And so this is kind of our first step in taking an alkane and putting a functional group on the alkane. Because for the most part, we either do this substitution reaction, which we will later call free radical substitution, or free radical halogenation, and combusting it. Combusting it doesn't really help us. Free radical halogenation allows us to build up more complicated molecules. And so we're going to spend a couple of days looking at free radical halogenation. And we'll do that probably in the next couple of weeks. Okay, so this is sort of a shorter lecture because these are the materials, but as I said, for Friday, if you're still having issues with the naming, Friday is a perfect time to bring those problems in, and we'll probably do some more naming problems in addition to, if you have any questions about this. The reading is pretty straightforward in the textbook.